Spanning trees hold lots of interesting properties about the total graph. Let's discuss one. So, spanning trees, as you know, are a subgraph G prime on the vertex set and a modification of the edge set, which is a subgraph of our total set, our total graph, such that G prime is a tree. This is nothing new, and on this graph here, we can see, for example, if we were to start at this vertex, travel like this, that's an example of a spanning tree. So we'll start with a simple unweighted graph. I'm gonna just draw one right here for you. Okay, so this is gonna be our base graph. And now what I propose we do is we're going to count, or we're gonna list out all of the spanning trees of this graph. All right, so we're gonna start by just taking the box and removing one edge at a time. All right, and then we got okay, so here we have the 8 spanning trees of this graph listed. You can look for more, but you won't find any. Okay, so next what we're gonna do is we're going to take each edge and we're going to assign to it a weight corresponding with the total number of spanning trees that use that edge. So for this top edge, for example, we have this graph uses it. That's 1, 2, 3, 4, 5. We have 5 spanning trees that use that top edge. Similarly, if we look around to any of the other sides, we can see if we're looking at this right side, we have 1, 2, 3, 4, 5. Bottom, 1, 2, 3, 4, 5. Left side, 1, 2, 3, 4, 5. And diagonal, we have 1, 2, 3, 4. Okay, so this is our weighting scheme for any unweighted graph. And what we're gonna do is if we assign a minimum path distance between any 2 nodes, that's actually gonna give us a metric space. Now, moving on, we're going to consider a barbell graph, or a graph that has 2 complete graphs connected by a single edge. So we're going to use K4 here. Again, connected by a single node. Now, I calculated this before, but if we were to look at the associated weights with any of the edges internal to these clusters, we're going to see that it has a weight of 128. If we were to look at this main edge between the two, we'll see that it has 256. Now this makes sense, right? Because every single spanning tree in this graph must use this edge when that's not true of any of the internal vertices, or internal edges, excuse me. Now, using this metric, we can kind of develop an idea of community structure within the graph. So now this is an intentionally very simple example, but you can see that each of the edges within these groups of K4s is only 128 units apart from each other. So they're relatively much closer to each other than any node is in this section than to this section. They're at least 256 units apart. Therefore, we can kind of see that we can break apart this barbell graph into two communities by this metric. And using visual intuition, that makes sense. If we have two complete graphs that are separated, we'd want them to be in the same communities. So you can see that by studying trees and the spanning trees of graphs, we can extract some interesting properties of the graphs themselves.